Hello, students. Today we're going to be talking about special right triangles.
Special. It says special there.
It's true.
I also cited my source, just saying.
You did.
The best.
All right, so this is the first type of special right triangle that we're going to look at. This is a 45, 45, 90 right triangle. I'm going to guess that in this picture, this is meant to be that 90-degree angle. And we call this a 45, 45, 90 because these two angles are each 45 degrees.
Is that an isosceles triangle, Mr. Carlson?
I believe that it is.
Sweet.
And I can see that this has been labeled so that we know that these two sides are congruent.
So it says leg one is 1 to start. So not X, but 1 to start.
Okay, so I mean, I guess that this side would be leg 2. Since we know those are equal, that would also be 1.
Oh, you got an easy one. All right. Now this is a right triangle. We talked about the Pythagorean theorem.
Mm-hmm.
So we got to do 1 squared, leg squared, plus leg squared is the hippopotamus squared.
Cool, I like it.
And everybody knows that 1 squared is 2. No, I'm kidding. 1 squared is 1, and 1 squared is 1. But 1 plus 1 is 2. So the hypotenuse is 2. Oh, no, the hypotenuse squared is 2.
There we go.
So then the hypotenuse is the square root of 2, because we take the square root of both sides.
Okay, so if I put that up here, think we try the second one? So if leg 1 is 2 and leg 2, well, we know those have to be the same. Would it be fair for me to just kind of fill out all of these for the leg 2, since we know those are isosceles?
So you're saying those all have to be the same? I agree. I say yes. So I'm going to fill in the Pythagorean theorem down here. We got 2 squared and 2 squared. So that's 4 plus 4. So that's 8. But we're not going to write it as 8.
Ooh.
So we're going to take 8 and we're going to do something called simplifying square roots, which we have not talked about.
That's true.
I'm going to show you. So 8 is 4 times 2. So I can write that as 4 times 2. And you should know what the square root of 4 is. The square root of 4 is 2. I can rewrite this as 2 square roots of 2.
Okay. So then we're on to the third level of this, which happens to be of length 3.
So that's 3 and that's 3.
And that would be 3, which means that that would be...
We just fought over erasing.
It's true. That'd be 18.
So the square root of 18, I can rewrite that as 9 times 2.
Yep, I agree with that, because 9 times 2 is 18.
The square root of 9 is 3. So that's 3 square roots of 2.
Okay. Can we do the same thing with 5?
Yes. So we got 5 and 5. I didn't try erasing this time. I thought you were going to do that part. So
we got 5 squared is 25, and 25 plus 25 is going to be 50.
So that's 50, but 50 is 25 times 2. Square root of 25 is 5.
Oh, so we could say this is 5 square roots of 2.
Yes.
Do you think our humans have noticed a pattern yet?
No. I mean, I hope they have. But if they haven't, we still love them. So let's do 10.
Okay, so that means anywhere that we have a 5, we're going to put 10.
Yes.
And I put a 5 again.
That's supposed to be a 10, Mr. Carlson.
Okay, and 10 squared plus 10 squared is going to be 200.
And 200 is 100 times 2, and the square root of 100 is 10.
I like it.
I'm hoping they figured out the pattern now, and we can just write this.
What? Oh, because it's whatever the leg length is times the square root of 2.
Yes.
I like it.
Sweet. Let's do more.
Oh, look, here's another type of special right triangle. This one's a 30, 60, 90 special right triangle, which is cool because it's really just half of an equilateral triangle.
So you're saying we should talk about, I'm drawing the right triangle here. We should talk about like that triangle if it shows up. Oh, there it is. That was exciting.
because if I cut that in half, we have 30. And then I've got a right angle there.
Wait, you cut it in half, right?
I did.
Okay. I have an idea about the length of DB then, but I'm not going to say it.
Is that because in an equilateral triangle, all three sides have to be the same?
Yes.
So
we just made two congruent triangles in there.
And this whole thing is 2x also.
Right.
Cool.
So if AB is 2, which is what it says at the beginning, so not 2x, but just 2, DB, I bet that's 1.
And that's because if the whole thing is 2, if we cut it in half, we get 1.
Yes. So I'm going to put a 1 there. So we got to do the Pythagorean theorem for AD.
Ooh, this is kind of tricky.
Yeah, because we don't know the leg. So we got to set it up different. We got to think about it.
So could we say that this is like leg squared, if I'm not writing an eraser, 1 squared plus the other leg squared is equal to 2 squared?
Yes.
It's a nice lag there in terms of showing up, huh?
Yes.
So we've got 1 plus leg squared is equal to 4. And I'm going to blow everybody's mind and say that the leg is going to be a square root of 3. Come on, there we go. Oop, almost there. Oof.
Almost there. Oh, there we go. Sweet. Okay, so we got square root of 3. Could I call that 1 square root of 3?
I think that would be pretty good. Okay, do you want to try the next number up?
Yeah, so if AB is 4, then that means that DB is 2.
Okay. And then
we can set up. Then we can set that up pretty well. The same way. So we got the 1 becomes a 2. The 2 becomes a 4. I'm just watching this happen. It's exciting.
So that's 4, 16. And this is going to be the square root of 12.
Square root of 12. So we can break the square root of 12. 12 is, wait, I can do this. 4 times 3, right? And then the square root of 4 is 2. So it's 2 square roots of 3. We didn't write the 1 square. I'm going to write that here. 1 square root of 3.
We forgot
and now
that.
we got 2 square roots of 3.
Okay.
So can we do the same thing? So we've got 6 now for AB. And if AB is 6, then DB is half of 6. I can do that. That's 3. So then we're going to have 3 squared plus leg squared equals 6 squared. 9 and then 36, right? And then 27. I almost said 25 because I was going to subtract wrong, but that would be
I almost did too.
It's a good thing I said it out loud. And then 27 is 9 times 3. Wait, the square root of 9 is 3. So that's 3 square roots of 3. Mr. Carlton, I'm starting to see a pattern.
I'm starting to see a pattern too.
Do you think they get it now?
I think they might, because I'm seeing 2 different patterns here.
What are your 2 patterns?
So the first pattern I'm seeing is because we cut this triangle in half, the length of DB is always going to be cut in half the length of a normal side. So where we had 6, we now have 3. Where we have 8, I think we're going to have 4. 10, we're going to have 5. 2x, we're going to have x.
Love
so
it.
Cutting all those in half.
Okay.
And then I notice a pattern that's completely independent of everything written on the right, because we seem to be just going 1, 2, 3. And oh wait, those are the same numbers that we see in the middle column.
It's true. There's just a square root of 3 next to them.
So this could be like 4 square roots of 3 and 5 square roots of 3. And I bet this would be x times square root of 3. So whatever that shorter side of this triangle is if we multiply it by the square root of 3, we get this taller side.
Love it. Okay, so we figured out some patterns. That's exciting. So now we have to draw a conclusion, or some people might say a jump to conclusion. So we have two different kinds of triangles. We have the 45, 45, 90 triangle, and then the 30, 60, 90 triangle. And I'm trying to think, those of us that have to take MCAS, there's an MCAS sheet, and I think they do x, x, and then x square root of 3. And then they do y, 2y, and y, sorry, thank you, square root of 2, y square root of 3. I was thinking ahead already. Apologies, that was a square root of 2, I agree. So I think those are the triangles you will see on the MCAS sheet, if I remember the letters correctly.
And you will always have it, and it doesn't matter if it's MCAS or on the SAT, they both give you these diagrams that have these proportions written out. One of the things that I like to think about is how do I get from one side to another? So if I'm going from like the short side to the hypotenuse of the 45, 45, 90, I'm multiplying by the square root of 2. And I like thinking about it that way because then if I want to go backwards, it's like saying that we're dividing by the square root of 2. And we have some other ways that we're going to talk about setting this up, but that helps me kind of process, do I want to multiply or do I want to end up making this smaller in that case? But we'll come up to that probably, I'm guessing, maybe in a couple slides.
We'll find out. It's going to be exciting.
What? On the next slide, we have to find this out. That's cray-cray.
It's like we predicted the future.
I know. Would it be fair to say that anytime that we see a 45, 45, 90 right triangle, it might be helpful for us to write this as x, x, x root 2?
Yeah, I actually don't like using x's because often in the question they have x's. And like in this one, they have x as a hypotenuse for b. So I like to use any letter I want. And I knew that you had written the x's, but they didn't show up. So we're doing smileys. I love it. Okay. So, and then I like to say, okay, what is equal to what? So we have a smiley face as a leg. And over here we have 9. So that means the smiley face is equal to 9. And if the hypotenuse is smiley face root 2, that means that the hypotenuse is 9 root 2. And we did that problem.
I like it. That seems like that was scarier looking than the math actually was for it.
It's true.
So could we do the same thing for the second one where we have, okay, here's a leg. So smiley face is equal to 2 root 2.
Yes, children, keep reading. It will be okay. Keep reading.
And that seems kind of scary, but I'm going to keep going. And that means that x is equal to smiley face root 2.
Yes.
So I'm going to put this in a different color. So we have 2 root 2 times root 2.
Oh, I see what you did. So we kept the root 2 from the smiley face root 2, but we had an extra root 2 from the smiley face.
And one of the things that I notice is that if I'm multiplying something by itself, that means that I'm squaring it. So this is like squaring a square root of something, which is kind of like doing the opposite thing of it. And I think that will undo that.
I agree. You could also do 2 times 2, which is 4, and then take the square root of 4, which is 2, if you're confused by the canceling out idea.
So this would be like saying, in fact, I'm going to change the colors because it's this 2 multiplied by that, which kind of gets combined into a 2.
Love it.
Which is 4.
Good. I was thinking 22, but that was wrong. So 4.
That's fair. Yeah, 22 is definitely not 2, but 2 times 2. Okay, I feel like this is a very similar problem to what we've been doing. Does it make sense that we use the same method?
Yes, it's similar, but it's a little different because you notice we have a number on the hypotenuse, like a 6. There's no root 2 there. And so it might be a little scary. So we can still do the smiley face idea. But in this case, we have a leg. So smiley face is equal to x.
Mhm.
So then that means that the smiley face root 2, which is the hypotenuse, is going to be x root 2, but that's also equal to 6.
Mm.
I wrote a 6 there, I promise.
I figured.
But now we have to solve for x.
So I know this is x root 2 really means x times root 2.
Oh, so we should untimes?
Yeah. So if I untimes it, we get that x is equal to 6 over root 2. And by the way, untimesing is another way to say division, which is totally, definitely untimesing is a real word.
It's true. By the way, that is a perfectly acceptable answer, but on like a standardized test, since they're written by old people, they do something called simplifying. What is it called? Rationalizing
Rationalizing
the denominator.
denominators.
That's the term. I was thinking simplifying square roots, but that's different. So 6 over root 2, what they're going to do is they're going to multiply that by its friend, root 2. And then we got to do that on top. So that's going to be 6 root 2 over 2, which is 3 root 2. And if I just blew up your brain, pretend it didn't happen and just pay attention to the thing in red, because that's fine for our purposes.
Mm-hmm. In fact, that's fine for all purposes. People who tell you otherwise are wrong.
It's true. It's true. I don't like simplifying square roots, but I know that it shows up. All right, so we got a softball diamond is a square.
That's a weird sentence. A diamond is a square.
It is. The distance from base to base is 60 feet. To the nearest foot, how far does a catcher throw the ball from home plate to second base? So that's like that vertical distance, which we're pretending that's a square. That was a terrible square, Mr. Carlson.
But it's a diamond square.
So there's some content knowledge that you have to have here. Like what the heck a softball diamond is. But it's a square like this, where you have first, second, third, and then home base. And this is the distance they're talking about. They're talking about throwing a ball that distance. Yeah, so we've got a right angle there because we have squares. So this is just an isosceles right triangle, right?
Mm.
So we got to go. Yeah, there we go. We got the smiley. I can't draw your smiley faces as well. So we've got the smiley face, root 2. And in this case, smiley face is equal to 60. So that means smiley face root 2 is equal to 60 root 2, and we did it. Although it says to the nearest foot, don't worry, I got you. So I'm going to multiply 60 by 1.414, which is obviously roughly that answer.
So it's going to be 85 point something?
Well, it says the nearest foot, so 85 foots.
Cool.
Sweet.
All right. Oh, look, we're switching triangles.
Oh, no. Can we still do smiley face? Oh, or should we do frowny faces or like straight faces or something?
I'm still going to do smiley faces. I like smiley faces. They're happier.
Not the one with no emotion.
Correct.
Okay. So in this case, you kind of have to rotate your perspective, or you could just, if you wanted to rotate the picture. Whoop. There we go. Now it lines up better.
Oh, look at that.
We have the side opposite the 60 as 5. So that means smiley face root 3. That's a 2, Mr. Butterworth. Root 3 is 5. Now, I'm going to note that D is going to be smiley face. Is that what you're just going to write?
Yep.
Oh, and 2 smiley face is F. So I want to note those things. So if I can figure out what smiley face is, then I can do the problem, no problem.
So I know to solve this.
That's multiplication, right?
Yeah.
So we have to divide again?
Yep. That sounds good to me.
Okay. So that means that smiley face is going to be 5 over root 3. And that's what D is. So D is 5 over root 3.
And 2D would be 2 times 5 over root 3. So would it make sense if we maybe simplify this a little bit more by saying this is 2 over 1?
Yeah. I think we need to write that, because I've had humans do like multiple
2 on top. Yeah.
Yeah.
And then maybe call this 2 times 5 is 10, 1 times root 3 is root 3.
Beautiful. And if you wanted to simplify square roots, you'd get 10 root 3 over 3. But you
If
don't
you want to
have to.
rationalize denominators.
Yeah. Why do I keep saying the wrong words, Mr. Carlson?
Because you're Cray.
I need to retire. I need to retire. That's it. Now I had to put this because obviously I'm from Wisconsin, and
True.
this has to do with hay bales. So a farmer's conveyor belt carries bales of hay from the ground to the barn loft. So these are bales of hay. If you've ever driven past a field, around here they often look like marshmallows because they wrap them in plastic, but they can also be rectangular prisms. The conveyor belt moves at 100 feet per minute. How many seconds does it take for a bale of hay to go from the ground to the barn loft? Whoa. This is crazy, Mr. Carlson. I don't know how to do this.
Well, thankfully, we're thinking about a plan and not actually solving anything yet.
Oh, that's a good idea. What part of the right triangle does the conveyor belt represent? The hippopotamus.
Oh, so this thing here, that is a conveyor belt.
Yes. That's bringing things into your house. Around here, they used to use such things to like do coal into your house. Not necessarily electronic conveyor belts, though. They could just be rolly belts.
Yeah, we used one of those when I helped unload trucks at Target for a number of years. One of the rolly belts.
Those are fun. I don't know what they're called. I used those when I was in the high school because we did a fruit sale. And to get the fruit off the truck, we'd set up this long rolly thing and just like fire them down. And of course, we were teenagers, and so probably wasn't safe. And
no,
whatever. Anyway, you know the speed. We do. It's 100 feet per minute. It says so. What other information do you need to find time?
Oh, so is this talking about some physics stuff? So we often from middle school talk about this as dirt because we have distance is equal to a rate times a time.
And if you don't understand what that means, pretend you're driving down the highway at 60 miles an hour. If you drive for 3 hours, you've gone 180 miles. Not around here because obviously you don't drive 60 miles an hour because there's too much traffic. But you could at places where there aren't tons and tons of humans. So we take the speed times the time, and that's the distance. So we know the speed. We're trying to find the time. So we need the distance.
That sounds good to me.
Got it. So we need this length.
That makes sense to me as well.
So this is just an artificial way of them trying to get us to use these 30, 60, 90 triangles, isn't it?
100%.
Got it. Do you think they put conveyor belts at 30 degrees?
No, that's very steep.
At least it didn't need 60 degrees.
30 degrees feels like a not so steep thing. If you walk up a 30-degree incline, you're going to be suffering very, very quickly.
You're super tired.
So here's my smiley face, 2 smiley face. That one came out like a monster. And then smiley face root 3.
So is the 12 the smiley face?
The 12 is the smiley face.
Oh, so 12 equals the smiley face. And we want to know the 2 smiley faces.
I agree.
So that's 24.
Okay, so the distance is 24 feet.
So we're done, right?
And we know this moves at 100. Oh, we have to find how long. So how many seconds?
So we're not done. Got it.
So we've got to then use this type of thing. So 24 feet is equal to 100 feet per minute times the time.
And we don't know the time, so we got to divide. So 0.24 minutes.
I agree.
And then there are 60 minutes in a second, right?
Absolutely. We are the worst.
Seconds in a minute. To be fair, I started to say it wrong and I just rolled with it. So 60 seconds in a minute. So we got to do 0.24 times 60.
Okay, so it's going to be 114 seconds.
114 seconds?
Well, it's 14.4, I think.
You are correct. 14.4. Did it. Cool. So that was an artificial application of this kind of triangle. Go us.
All right. So these are some problems to practice. Are these ones that we think students would try on their own, or the ones that we want to go through together?
I think they should be able to do them. I think they should pause the video once we stop talking in a second, and they should do them all, but
Mm,
we will also give them the answers because we're going to be magical and show you all the answers, but we're going to do them live really fast.
it's true.
I just put pressure on us in case you're curious. Okay, so pause the video and do these problems.
Nice job pausing. Welcome back.
Hello.
Do you want to do the two on the left? I'll do the two on the right.
Sounds good. That's going to be 5 root 2, which is 5 times 2, which is 10.
Done.
And then that's 60. Oh, I have to think here. That's 60. So this is going to be root 2 times root 3. No, root 2 over root 3. Goodness me. Root 2 over root 3. And then this is going to be 2 of those. Can you check that? Because my brain just fell out. Did I do that right?
I like it.
Okay. That one was hard. That one made me pause for a minute. Darn you, Mr. Carlson, for giving me the hard one.
Cool.